All right, so let's get started. Today, I would like to welcome Zach Diermyer from RIT in the Astrophysical Sciences and Technologies program, where he is a BS/MS student. And today he'll be talking about his work with Breakthrough Listen. So take it away, Zach.
All right. Thank you, Jesse. So yeah, as Jesse mentioned, I'm Zach Diermyer, graduate student at Rochester Institute of Technology in Rochester, New York. So today I'll be talking about the research I've been working on with my advisor, Michael Lamb. And this is the research I'm doing for my master's thesis. It's a spectral component analysis of the repeating FRB 121102. This is the first discovered repeating FRB, as we'll talk about. There's a new standard for naming FRBs where you include the full year. So FRB 20121102, if you see that name, it's the same FRB. So yes, naming conventions aside, I'll be calling it 121102 for the talk. So without further ado, I'll get right into it. Maybe. There we go. So starting off, I'll just talk about what is an FRB. FRB stands for fast radio burst. It's millisecond duration radio signals. They're extremely bright at their source, and all sources of FRBs confirmed so far are extragalactic. We can tell they're extragalactic by their fairly large dispersion. They have huge dispersion measure, orders of hundreds to thousands, I believe. And so I have some statistics of published FRBs and how many are repeaters with how many have localized host galaxies over here. But CHIME has been working wonders. You can see from the sky map I have down here, CHIME has discovered over 1,000 FRBs in their data. They just haven't published them yet. So yeah, FRB science is picking up. It's a really great time to study these. And yeah, I love doing this research. So FRB, getting back to what FRBs are. FRBs are transient events. Most of them are just one-off. However, some have been observed to repeat. So making the distinction, we have repeaters and non-repeaters. So apparent non-repeaters are the ones that are truly transient, have only been observed once. They usually have a shorter duration, only about a millisecond, order of a millisecond or two. Whereas the repeaters, they will have a longer duration, 10 to 20 milliseconds, tens of millisecond order. And the big important part about repeaters is that their bursts show a component structure, which I will talk about for most of this talk. This is what I've based my research on. And also an interesting thing about these repeaters is that they have what's called a pseudo periodicity. This isn't something I work on, but I find it very interesting, so I included it here. The pseudo periodicity is sort of a modulation of their activity, it appears, where they have these active phases. The sources have an active phase where they're burst over hours or days, and then they'll turn off for some amount of time. CHIME discovered the second repeater called 1809-16, and that has an exact 16.35 day period or modulation. And then it'll burst for a few hours and stop for another 16-ish days. There's been some research on the FRB source topic of today, 121102. And that one, it may have a active phase period of about 154 days, but this hasn't been truly confirmed yet. So this kind of weird activity implies that maybe all FRBs repeat, but some of them just have timescales that are just too long for us to observe. Years, thousands of years even, who knows? So yeah, there's repeaters and non-repeaters, but non-repeaters may actually repeat. So that's an interesting fact. Putting that aside, we'll get into what I'm going to talk about today. And the big question is, what are FRBs? we still don't know what the progenitors are. So we don't know what source object triggers these things. Sorry, one sec. Okay. So for what are FRBs, there are plenty of different theories. They range from something like asteroids impacting neutron stars, all the way to exotics like cosmic strings or extraterrestrials. Um, I'm going to base what I talk about on a rather simpler model, just a neutron star trigger and maybe some sort of surrounding medium, like you can see in this diagram here in the middle. So we want to know exactly, do the bursts from these fast radio burst sources, do they come from the neutron star itself, assuming it is a neutron star, or do they come from the surrounding medium? So are we observing a burst from that surrounding medium or the neutron star? And understanding what true proportion of bursts of these fast radio bursts have the component structure I mentioned previously will give us a little bit more of an understanding about what physical mechanisms cause them. And it can help us to answer this question of where do FRBs come from? And this model here with the neutron star surrounded by some sort of medium probably has some relation to this source, the 1809-16 source, because it's embedded in this V-shaped star forming region of its host galaxy. So you can visualize that this diagram here could potentially be this source, the second repeating FRB that we discovered. So that's the motivation, that's our theory that we want to apply my research to. And so you may ask, why choose the neutron star model out of the many theories that exist for FRB sources? Well, last year, April of 2020, in early pandemic times, we got this amazing signal from the universe. Up here, this was a radio burst that came from a magnetar in the Milky Way called SGR 1935. So this magnetar had a radio burst that was extremely bright, very bright, almost at FRB luminosities. So this phase, I included this phase space down here because I think this gives a great visualization of this. It's frequency width on the x-axis, horizontal, and then like radio luminosity on the y. And fast radio bursts sort of exist up here. It at very high luminosities and relatively narrow frequency widths. And the SGR 1935 burst was in the same frequency width, but just a few orders of magnitude lower in luminosity. So we can't really say that it is an FRB, but it has the same general location on this phase space. So it's likely that it could produce an FRB type burst at any time. I believe people have had follow-up observations of this source multiple times, and it's bursted, but not quite any more powerful than this burst. So we're still waiting to see, waiting to confirm that that magnetar fast radio burst theory. So now I'll talk about the repeating FRB that I've studied, FRB 121102. It was the first discovered repeating fast radio burst source, and it's more extreme. It's very active. We've had hundreds of bursts detected from this source so far. I'm not quite sure exactly how many, but it is a very active source. It's also in a very magnetic environment. It has a rotation measure much, much higher than other FRB sources, orders of magnitude higher. And it also has a persistent radio source coincident with it. So over here, this image on the left, this is an image of the host galaxy containing FRB 121102. The source is at this black plus here. and the persistent radio source is over here with the red line. So this persistent radio source could be the cause of this extra activity. I don't particularly mind the extra activity because it gives me more to work with. So I like that. But we're going to be talking about this today, and we'll be looking a little bit at its burst structure and how it can relate to the theory. Before I talk about the data, I'll mention where it came from because this is very important. The breakthrough listen data, it was taken at Green Bank in August of 2017, back when I was just about to start my sophomore year as an undergrad, which seems like a long time ago, but it really wasn't that long. So the C-band receiver was used for the entire 6-hour observation window, and a lot of great data came from it. And I've been working with that data for my research. So thank you all. All right, so here is the data. I've included some data plots here that we're going to look at. In the original breakthrough listen data, Vishal Gajjar, he found 21 bursts above a signal to noise threshold of 6. And 2 of these bursts show what is called a component structure. And the component structure is a separation of subbursts, subbursts of the total signal that are separated by time. So here we have burst 11A at the top. It has 4 components, which are these yellow signal, vertical yellow strips of signal that have this strange separation in time. So 2 of the 21 bursts originally detected, originally found above the signal to noise threshold have this component structure. 3 are what are called unresolved components. So they may have an underlying component structure, but they're too noisy really to tell. Burst 11A has a very high signal to noise and very clear defined components. But burst 11E down here, this is one of the unresolved multi-component bursts. It has a structure that could be multi-component, but it's just too hard to tell with all the noise. And then the rest of them, the other 16, if I did the math right, I hope I can do that math. The other 16 are all single component. So they just have one very, very small duration burst, one small signal emission. So yeah, and then after that, after these 21 very bright high signal to noise bursts, Yunfan Zhang found another 72 potential FRBs using a machine learning approach. And that's something I'll talk about at the end. But that leads to a potential of 93 FRBs in the breakthrough listen data. So a lot of good data to look at. This is something a little funny. I think it's included in almost every FRB talk because it's a good joke. Not joke. It's a real thing, but it's funny. So we have this thing called a sad trombone structure. It's kind of where these components march downwards in frequency. So they'll start at a high frequency, like burst 11A. And then as we go later in time, the components will go to lower and lower frequencies. So if you were to say, play an instrument using sound scales with frequencies like this, you would have sort of this descending notes. And this is a structure that's seen in a lot of repeating FRB bursts. Many repeating FRBs have component structures, and they can move all over the place from high to low frequencies back and forth. But a lot of times we see this sad trombone structure, and they will look like this. I have a sound here of the sad trombone. I can't figure out how to get it to play over Zoom, but when I play it here, it echoes on my laptop, so maybe you'll hear it very faintly. Okay, So that's what it sounds like. If you didn't catch it, you can just Google it. And it's pretty infamous. Very notable sound. So yeah, digging a little bit deeper into these components, what I actually do with them. First, I just start with fitting them out. I take each frequency channel and I fit Gaussian curves, one Gaussian for each component. You can see here at this really bright knot in burst 11A, I fit 3 Gaussians for each component. Um, and then just going up here to this image, these are kind of the images I show to show where my fits are located. So each of these magenta lines sort of traces the centers of each of these Gaussian fits. So it makes it very easy to see, to pick out the 4 components in burst 11A here. And at the moment, I have unresolved multi-component bursts just fit with 1 component. Since it's not clear whether they have a multi-component structure, I leave them as single components for now. But I'll touch back on this again at the end. So once I fit the multi-component bursts, once I fit all the bursts and fit out their components, I can get a fluence distribution, like this plot here on the left. This is the fluence distribution, again, for burst 11A. So for each component, you can see its fluence versus frequency. These are approximate. I haven't done any error analysis yet, but they do wiggle and jiggle quite a bit. It's approximate, but it doesn't need to be completely accurate for my analysis. So yeah, I find these fluence distributions, and then the big thing that I want to do with these is to really use them to analyze the structure of bursts, of fast radio bursts, and of their components specifically. So to do that, I find the statistical moments of this distribution. So those being variance, skew, and kurtosis. And I just make a scatter plot of the total fluence, all summed up, versus the values of those moments. So for skew specifically, just looking at skew, it's one that I picked out for this talk. You can see that the single component bursts with the blue dots are kind of grouped towards 0. This is something that I haven't concluded yet, but they seem to average towards 0, whereas components of the multi-component bursts, those being burst 11A and burst 12B, can have sort of more of a widespread range in values. So burst 11A, you can see ranges from negative 0.75 skew up to 0.5. It just has like a wider range. And also with kurtosis, you get a very wide range, whereas the single component bursts just seem to group up towards lower values. So with this information in mind, my next step is to reduce the signal to noise of multi-component bursts to see if they become more like single component bursts when their signal to noise is reduced. So I just add white noise, random white noise to those multi-component bursts. You can see here at the top, this is burst 11A with added noise. And first I add noise until I've reduced the signal to noise to the average of single component bursts, and that's this big plot down here. So the signal to noise of burst 11A and 12B reduced to the average, one of the components, first of all, for burst 11A is washed out, so it can't be picked out by the fitting routine I use, and that leaves us with 3 components. And interestingly enough, these 3 components seem to group towards lower values of skew, more towards where the single component bursts are grouped. 12B still stays at sort of a maybe higher value, but it's kind of hard to tell. And when I keep reducing the signal to noise until there's just 1 component left, again, it's hard to tell. Burst 11A goes out towards higher values yet again. And kurtosis actually does the same thing. So I didn't include the kurtosis plot here, just so that way I wouldn't overload it. But kurtosis actually, when the signal to noise is reduced, all the components will group towards lower values, just like where the single component bursts seem to be grouped. So this is an interesting result. So this could mean that these single component bursts that we see could have a multi-component structure, an underlying structure to them, that we just can't observe because of noise. So this has great implications for theory, because 2 out of 21 bursts having a multi-component structure isn't very significant. But if the true proportion of bursts with component structure is greater, or much greater even, this leads to a lot of implications about the underlying physics behind the source itself. So this is where I'm at. It's inconclusive at the moment just because there's so much variation here. But that's what I'm going to be working on in the coming months as I get ready to defend my master's thesis, sort of populating these scatter plots a little more. And that is where I moved to the extended data set. So I mentioned that Yunfan Zhang had found many bursts, potential bursts, using machine learning. And so I've been working on analyzing these. The problem is because they use a lower signal to noise threshold, only a signal to noise threshold of 3, the bursts are very hard to find. Even though I have the timestamps of where they should be in the data, they're just very hard to find. I included the first one here. I just called it burst 11A1. It's this very tiny, this one bin here, if you can see it. So even though it's able to be picked out, there's not much structure there. So without structure, I can't use it for this analysis very much in any helpful way. But there are other bursts. This one I've called 11B2, which do show some structure and can help me populate those scatter plots, hopefully to get a better statistical conclusion over whether the multi-component bursts do tend to group up with single components. And then something else that I've been planning on working on soon is fitting the unresolved component bursts as multi-component. So far, like I said, I've only fit them as single component, but I can fit them as multiple components, just giving them some sort of a cutoff in between where the components should be, or looking at them where they should be, and just seeing where that leads to. So in summary, hopefully I didn't go through that too fast, but I take these bursts, these fast radio bursts with multi-components, fit them, see where their statistical moments lie on this sort of a scatter plot, and then I reduce their signal to noise and see if they group up more towards values where there are single component bursts, in an attempt to find if the true proportion of bursts with multiple components is higher than observed, greater than observed. And if it is, then this could be a great implication for our fast radio burst theory. It'll help us decide which ones are more likely in a physical sense than others. So thank you all for listening, and yeah, I'll stop there. My cats are playing with a rock. I'm sorry if that's loud.
That's all right. It was mostly in the background for your talk. So yeah, thank you very much, Zach. That was a great talk. And I realize it's probably the first time I've actually gotten to hear you talk about your work.
Yeah.
Since our time at RIT didn't overlap very well.
Yeah, unfortunately.
All right, well, I see Ryan has his hand raised, so I will let him go with the first question. And if anyone else has a question, again, raise your hand, or you can submit in the chat below.
Yeah, thanks for a nice talk.
Thank you.
So I have 2 questions. The first is, how scalable are the techniques that you are using to kind of figure out what these fluence distributions are and compare them to single component bursts? And the reason I'm asking that is I'm wondering if this could be applied to a really large data set like the ones that are not coming out the chime, where you just have a lot more statistics from more repeaters, and not just repeaters, but non-repeaters with single component bursts, and whether or not you could try and look for any trends there. And I'll let you answer that, and then I can ask my second question.
Yeah, okay. So I think that the process is fairly fluid. I think you could apply it to different sources. Unfortunately, I've only made the code to work with this data. I'm not sure if it'll transfer to other types of data, but that is something I could work on as well. If I were to get data from, say, Chime on 180916, I'm sure I could work it around to get it to make it work with that as well.
Yeah, I mean, I think that'd be interesting because you're working with like a decent number of bursts here, but still, if you really want to pull out really robust statistical results, having the kind of samples that are becoming available with things like Chime would be great.
Yeah.
The other question is whether or not you've given any thought to looking at how the distribution of fluences and any of the other properties you can pull out align with some of the different models where they make predictions about the types of timescales and frequency drift and all the different aspects that you see here. I'm thinking specifically of some of the models that involve interstellar medium, or the medium around the source of the fast radio bursts, kind of modulating the emission in these ways.
Yeah. So I think. Sorry, 1 second. Let's see. So the Zhang bursts, they have been kind of sorry, the cats are playing with something. Okay. So, sorry, could you repeat the question? I didn't mean to get distracted by the cats, but they are going nuts.
So just, I mean, in brief, can you use the statistics that you're pulling out to compare with some of the different theoretical models that do make predictions about the types of distributions that you should see in the various different properties of the bursts?
Yeah. Oh, yeah. So the Zhang bursts, they were interesting in that they sort of all seem to come at certain peak frequency ranges. So I think 7.2 gigahertz and about 5.5 gigahertz. And the peak frequency ranges did seem to have some sort of a relation with their width. So lower frequency bursts had like a much wider bursts than the higher frequency ones. I'm not sure, and that's something I was also thinking of looking at, but I'm not sure how much I can get done before I have to defend my thesis. If continuing this, that is something I would look into, and yeah, potentially other frequency drift related things. They could be, they're very important for whichever theory applying to certain theories. Yeah.
Great, thanks.
So, it looks like there were some frequency ranges where there actually was never a burst found. Is that just a signal to noise issue that, I mean, like the edges of the band didn't seem to have any bursts in it? Is that, do you think that actually is a real feature of this cause of the bursts, or are they actually just a signal to noise issue so you don't detect anything on the edges?
Yeah, as far as I could tell looking at the bursts, so some of them did go past the 8 gigahertz, the end of this band, but I don't think I've seen any in the lower region. There are 1 or 2 that push down towards lower frequencies in the band, but yeah, most of them are at higher frequencies, especially in their peak frequency. It exists at around 7 gigahertz.
All right. Well, if anyone else has any questions, please raise your hand. In the meantime, I had a question for you. As someone who's not terribly familiar with fast radio bursts, I was wondering if you could talk about or have any explanation as to why this sad trombone feature exists so commonly in fast radio bursts, and if what does it look like when they don't?
Yeah, so I have, I'm not quite sure why it's a sad trombone. I haven't dived too deeply into theories. I've only read a couple papers so far. But the sad trombone just shows up the most, and I'm sure there's some underlying physical mechanism for that. As I look more into theories, I'll probably find it. If they don't have a sad trombone structure, that's where things get really weird. Some of them can go from low frequency up to high, back to low, bouncing around like that. Others have what's been called the happy trombone now, where they start at low frequencies and go up to high ones. So yeah, it's strange, and I'm not sure why it's the most often observed structure, but it seems to be the case.
Okay, so presumably it would be tied directly to whatever the formation mechanism of these outbursts are.
Yeah, that would probably be the case.
Okay, and do we have any other questions from the audience?
Just a quick comment on that. So it could be intrinsic to the source. It may also be something about the intervening medium. So you see similar structure in some pulsars where you get basically lensing of the signal by discrete kind of dense structures within the local ionized gas. So there was a paper about this with the Black Widow pulse, one of the original Black Widow pulsar, which goes through these eclipses. So I think that's one potential interpretation, is that it results from plasma structure in the regions around the fast radioverse.
Okay, thank you. I'll have to look into that. I haven't, Michael Lamb hasn't mentioned that yet, but I'll ask him about it when we meet next.
They're really making a lot of noise back there.
Yeah. Well, I was hoping they'd be quiet, but why would they?
No, never. And as Michael Lamb points out in the comments, apparently a dangerous topic to discuss.
Okay.
So clearly there's more to it than that. Excuse me. All right, so any last opportunity for questions to our speaker, Zach? Speak now or, well, contact him later. All right, looks like everyone is quite happy with everything you've had to say. So I think we will end it a little bit early. So thank you very much, Zach, for speaking with us today. And
Thank you for having me.
of course. And for those of you interested, you can tune in next week where our speaker will be Victoria Butler. Have a good rest of your week, folks.